Okay, so this takes us to insertion sort, which, as I indicated earlier, is a little bit more subtle than the other two basic sorting methods. So let's take a careful look at insertion sort. Let me remind you that the strategy is to go through the array from left to right, and as we proceed through the array from left to right, we want to somehow rearrange things to keep the initial portion from the beginning up to where we are right now sorted. Okay? So that way, by the time we get to the end of the array, the entire array guaranteed to be sorted. I previously said that like the other two sorting algorithms, it requires multiple passes. And upon thinking about that again, that is a matter of semantics. You certainly could say it's multiple passes, but I think it's best here to think differently and to regard the outer loop not as counting, so iterating several passes through the array as we did with bubble sort, as we did with selection sort. Instead, think of the outer loop as, well, we're just taking one pass through the array from left to right, and after each step forward, we're pausing to look backwards and rearrange the array from the beginning up to where we are right now. Okay? All right, so we see the loop counter, the outer loop counter I goes from 1 up to n, and it stops when I gets to n. Okay, the body of the loop copies what's in position I of the array into a local variable, TMP, temp. This is done because in order to maintain or to force the correct ordering of the initial portion of the array, it's going to be necessary to sometimes shift entries from left to right. And so what's in position I in the array right now is quite likely to get overwritten in a moment inside that inner loop. And if it does, we don't want to lose the value that's in P bracket I. Probably it would make it a little bit simpler if we think about a particular pass through this array. So why don't we pretend that we've already gone through, let's see, four passes of the outer loop, and that right now I is equal to 5. Okay? If everything works correctly as I've indicated that it should, as it must, everything before position I should be in order at this point. In other words, P bracket 0 should be less than or equal to P bracket 1, which should be less than or equal to P bracket 2, which should be less than or equal to P bracket 3, which should be less than or equal to P bracket 4. But now we're looking at P bracket 5, and there's no telling what relationship P bracket 5 stands, how that stands in relation to the previous entries. Okay, so here we go. We copy what's in P bracket 5 into temp. Okay, now we start this inner loop. The inner loop has a loop counter J, which is initialized to I and which is decremented each time through the loop. So this is going to basically allow us to do some backwards looking through the initial portion of the array, as we'll see. Okay? The continuation condition here is a little complicated. There's two parts. It's an anding together of two parts. But the first part is very simple. It just says j greater than 0, and that's just there to avoid letting j decrement too much and run past the beginning of the array. Okay? The more interesting part is the second part, which says that this loop should continue if j is less than p bracket j minus 1. Okay? So why don't we just start this and see what happens. With I equal to 5, j will initially start off being 5 as well. Okay? So what happens if temp is less than p bracket 4? Okay? Well, if that happens, then the body of the loop says to copy what's in position 4 into position 5. And that's absolutely a correct move. That's the right thing to do. Why is that? Because we're only gonna be here doing this if temp is less than p bracket 4. So that means what's in p bracket 5 is less than p bracket 4. That must mean that p bracket 4 is the biggest of all the entries that we've seen so far. Because p bracket 4 is bigger than, it's at least as big as everything before it. And now we're saying, well, if it's actually bigger than p bracket 5, okay, then it's the biggest. And if it's the biggest, it should be put into position 5. And so that's indeed what the inner loop has accomplished so far. It's copied what's in p bracket 4 into p bracket 5. All right, I think you see it. Then j gets decremented. All right, so now j is 4. J is 4. All right, so what happens if temp is less than p bracket 3? Well, then, of course, it's going to cause what's in p bracket 3 to get copied into p bracket 4. It's basically shifting that over to the right one. And that's also correct, okay? Because temp is less than p bracket 3, so temp should come earlier. All right? To make that happen, we're going to have to take what's in position 3 and shift it over to position 4. All right, j gets decremented again, so now j is 3. All right, what happens if it's not true that temp is less than p bracket 2? If it's not less than p bracket 2, so in other words, p bracket 2 is less than or equal to temp. Okay, well, if that's true, we don't want to move p bracket 2. P bracket 2 is actually currently sitting where it belongs. Okay? And it's time to quit this loop. There's no need to look earlier. Okay? We'll just keep seeing things that are smaller than temp, and that's pointless. All right, so the inner loop terminates, and what's in temp gets copied into p bracket 2, and that's exactly where it belongs. What used to be in p bracket 5 has now moved into, excuse me, I meant to say position 3. J is equal to 3. J is equal to 3. So we're taking what's in temp and copying it into p bracket 3. We're taking what used to be in p bracket 5 and putting it into p bracket 3. And of course, what used to be in p bracket 3 is now in p bracket 4, and what used to be in p bracket 4 is now in p bracket 5. And now we can safely say that everything from p bracket 0 up to and including p bracket 5 is correctly sorted. Okay? The process continues. On the next iteration, I will be 6 and play the same game. And that's it. When we get done with the outer loop, the entire array is sorted. I'm going to take a brief pause here from what I actually have content-wise on this slide, just to insert something that is going to get mentioned later, but I'd rather say something about it quickly here. We did a careful analysis earlier of bubble sort and basically said, well, we can count the number of comparisons that need to be made in bubble sort, and that count is the same regardless of the array and the order of the entries in the array that we start with. Okay, it's basically we saw capital theta of n squared comparisons that need to be made no matter what the array looks like. Okay, and that leads to a time complexity of capital theta n squared. It basically takes capital theta n squared amount of time to sort using bubble sort. Okay, and very similar reasoning, almost exactly the same, can be applied to selection sort. Once again, it is basically because you have an outer loop and you have an inner loop, and you wind up counting 1 plus 2 plus 3 plus 4 plus ... up to n minus 1 or possibly up to n, doesn't matter, and you end up with capital theta n squared. Okay, I want to get out of the way right away that can happen with insertion sort too, but insertion sort is different in that the inner loop will run for a period of time that could be very short or quite long. It all depends on the nature of the array that you start with. I think if you think about it for a second, you'll see this. Suppose the array is already in order, then when you insertion sort, the inner loop will always terminate very, very fast. In fact, you'll never execute the body of the inner loop at all. Okay? Consequently, it really just boils down to going through the outer loop. Okay? So, you do the outer loop n times, and you wind up saying that in that case, the amount of time it takes to do insertion sort is capital theta of n, not of n squared. But that's in the best case. In the best case, insertion sort takes capital theta of n amount of time. All right? In the worst case, insertion sort will take capital theta n squared time, just like the others, because in the worst case, say if the array is in completely reverse order to begin with, then the inner loop will have a lot of work to do, and it will have to run all the way through the initial portion of the list each time. Okay, so in that case, you wind up in a situation very similar to bubble sort and selection sort. And so in the worst case, insertion sort does capital theta n squared. Okay? It turns out, on average, insertion sort does capital theta n squared. Okay? For an average array, let's say. Okay. Those three algorithms stand, which on average, all three of those on average, take capital theta n squared time. Okay? They stand in stark contrast, really, to the next two algorithms we're going to look at, whose time complexity is a heck of a lot better. Okay? So these other two algorithms we're going to investigate are called merge sort and quicksort. And both of them, we'll start with merge sort, both of them lean heavily on recursion. And frankly, they would be difficult to explain without recursion. The strategies are more complicated, they're more subtle than the previous three strategies, but the power of recursion makes each of them, merge sort and quicksort, not so painful, pretty easy to explain. However, that depends intimately on understanding recursion. So if you don't already have a good grounding in recursion, you really need to take a serious time out from these lectures and go study recursion and deal with quite a few early examples, such as computing n factorial and some of these standard examples. Come to terms with recursion and then return here, because honestly and unapologetically that there's really no way to get your head around merge sort and quicksort and everything and quite a bit of material coming at us in the future without a really good sense of recursion. Recursion is a very powerful and wonderful tool. Okay, a tiny detail concerning merge sort. It requires extra memory. We will assume that there's an extra array available to us. We'll call it the auxiliary array, and we'll basically use that as a scratch pad. We'll be copying from the original array back and forth to this auxiliary array. And because of the need for this extra memory, it's frequently said that merge sort does not sort, quote unquote, in place. Okay, yeah, but letting the cat out of the bag right here, we'll do a time complexity analysis in a little bit and hopefully convince you, so it's very important that we convince you, that merge sort has a time complexity of capital theta n log n. And of course, n log n is better, quite a bit better than n squared, because log n is much less than n when n gets big. Okay? This required time for merge sort, capital theta n log n, is true in the best case, in the worst case, and also on average. Okay? Hoping that you remember binary search, it's similar to binary search in one respect, namely, it takes a list or an array and chops it in half, and then attacks. In the case of binary search, you just look at one of the two halves and ignore the other half. The difference here is with merge sort, you have to actually process both halves, and we'll do that recursively. So don't worry about binary search. If you forget it, that's fine. The important idea here is that merge sort is going to work by taking an array that you want to sort, cutting it in half, and then recursively sorting each half. Okay, it's basically going to call itself twice, once to sort the left half and once to sort the right half. Okay, all right, that accounts for, well, there are two recursive calls there, but that's one level of version. Okay, you start with an array of length n, and you chop that, and you have two subarrays, each of length n over 2. Each of those subarrays of length n over 2 have to be recursively merge sort. Okay, that takes us down to one level of recursion. But then each of those gets cut in half. You end up then with arrays of length n over 4. You take something of length n over 2, cut it in half, you get arrays of length over 4. And now you're down at another level of recursion. And then, of course, the arrays of length n over 4 get cut in half and to produce arrays of length n over 8. And by the way, I'm assuming n is big, and well, I'm not worried about rounding. Obviously, you have to round here. If n is not a power of 2, then you need to round either up or down. But essentially, you're cutting in half. You're trying to cut into two pieces of nearly equal length. Equal if you can get it, nearly equal if you can't. Anyway, how many level of recursions are required? Well, I went from n to n over 2 to n over 4, and talking about the lengths, the sizes of the subarrays. The original one is length n. Then you have to deal with subarrays of length n over 2, then subarrays of length n over 4, then n over 6, n over 8, then n over 16, and so forth. And the question is, if n is a power of 2, like 16, then you're going to go what, 4 levels down? Okay, so what is 4 in connection with 16? Well, 4 is the base 2 logarithm of 16. And in general, it's going to take approximately base 2 logarithm of n recursion levels, right? Levels of recursion. All right, so more about that later. The depth of recursion is about base 2 log of n.